Alright, guys, how you feeling?
Like I cannot update it anymore. So I just stop there, yeah. Yeah, I'm gonna stick with you until you're gonna die. I'm gonna use all the money that I spent. I use it. Take care of it.
I have like my screen lights every time I'm done. And I'm like, I just have a screen protector. Like, I don't want to this is like the it pairs this. So like, okay, so I have a screen protector. I have this.
You had it.
And this. I mean, that's kind of dirty.
If you keep it this way, it is going to last for 20 years.
Alrighty, everybody. So we are going to get started. Hopefully, do I have the camera pointed at the wrong screen? Oh no, it's just really delayed. I'm looking at the YouTube instead of the YouTube is delayed like it's delayed like a few seconds, probably in case some shenanigans start happening. They can. Well, who's they? Nobody's watching this except for 5 people. Wow, there's 5 people. Yeah, so today, the homework is due today. You can turn it in paper or online. It doesn't matter to me. Personally, I prefer paper, so if you got it on paper, but it doesn't matter. It doesn't matter. I'm just saying that when I'm grading stuff, when I'm grading it, my biggest problem is I don't like the interface that Canvas has to provide feedback on the electronic stuff. So like, one, you have to use the iPad or you have to use a tablet. If you try to use the desktop version, it doesn't, like any of your like little lines that you write, each one is like a separate comment or whatever, and so it doesn't save them. It's really meant for like a tablet type device, which I have an iPad that the university bought me that I use for that, so that's fine. But it just, I don't know, it's not the same. It's a lot easier for me to do it. So I'm not saying to print it out or anything like that. If you got it electronic, do it. But if you got it printed out, it's just, I just as soon you just turn it in as a physical paper. So why don't you just leave those on the back of the class when class is over, and we will do that way. So other things to note, I'll post the lab probably tomorrow. I have to tweak it quite a bit because the equivalent lab last year started adding pieces to the project, and we're going to do that for this lab too. And I already told some of you what we're doing. So we're basically this lab 2. First of all, everybody's going to have time at the beginning of the lab to finish up lab 1. Lab 2, we're going to start building an op-amp circuit. So we're going to start building a circuit that maintains a constant current flow to a load. And we're going to kind of, in lab 2, we're going to build a constant current op-amp driver with, and we're going to investigate methods to sort of stop when the voltage gets too high. So the idea is, the goal for lab 2 is going to be build a circuit that maintains a constant current into a load and that stops the flow of current at a certain voltage level. So once the voltage gets to a certain point, it stops it. And there's several ways to do that, and we're going to sort of investigate them in the lab. But that's what's going on, but I'm kind of tweaking the details of the changes right now. But I'll get that posted. It shouldn't, again, you're not going to need a pre-lab for lab 2. And most of what people are going to start on Thursday is they're going to start with finishing up lab 1, but that's the rest. But again, if you didn't bring your breadboard, if you borrowed a breadboard, you're really going to want a breadboard starting this week because the circuit that you build, you're not going to disassemble it. The circuit you build this week, you're going to want to keep it. And actually, if you're working with a partner, you don't have to have 2 separate breadboards, but you might prefer to each have your own separate circuit that you build. So if you each have your own separate circuit that you build, then if your projects decide to, because you have some flexibility in your project design, if you as a lab group decide to divide off, you don't have to right now, but if you decide to each sort of do a very different circuit, then you're going to each sort of have to build that, and you might be more comfortable if you just already have your circuit kind of pieced together. So that's just the heads up on that. For today, we're going to, so again, I'm going to kind of rely this semester on people watching the videos. If you didn't watch the videos, you're probably going to want to watch them shortly after the lecture, or part of the lecture probably won't make sense. You can always re-watch it today. So I was planning on starting to do homework problems from homework 2 today, using the homework problems as a way to talk about the content. So I'm going to quickly just talk about input impedance, which we talk about in the videos. I'm going to quickly talk about problem 1.6, which a lot of the problems in this book are sort of like the hardest part of the problem is determining what the problem wants from you. And so once you get, which sometimes you have to determine by inference, and sometimes you have to just guess. But keep in mind that when Franco was creating these problems, he wasn't putting that much effort into it. He was doing it. So he wasn't trying to be crystal clear with what he's asking for. He was sort of saying, you'll get it. Just. And so some of the questions leave some ambiguity, and students don't like that. So, just to be clear, when I give you problems on an exam, they are much more clear than the way he presents them. So there will be nothing implicit, because if you have to imply what I'm looking for in a homework problem, in a test problem or midterm problem, then everybody's going to imply something differently, and it's really tough to grade. And my goal with a midterm is to have it be as easy to grade as possible, which means clarity, conciseness, and consistency. I'm okay if everybody gets a problem wrong, but I want them to get it wrong the same way. I'm just kidding. But the biggest thing, the biggest takeaway, all the stuff we investigate in chapter 1 is really important. Functionally, practically, and the thing that I'm going to ask you the most about on midterms is the basic question of, here's an op-amp circuit. Tell me what the op-amp circuit's doing. Tell me what the output voltage is of this circuit. And then the add-on being, okay, tell me what the output voltage is going to be in the non-ideal case where this op-amp has a finite open loop gain of 1,000 or 10,000 or something like that. So that's the biggest thing is, the book has you explore a bunch of weird random things, and they have questions that ask for weird random things, and they have problems that make you do this, and they're all useful for understanding op-amps, but the big takeaway that I will be testing you on is, can you identify what an op-amp circuit does, what the output voltage is, and can you tell me how a non-ideal open loop gain impacts that output voltage? Okay. So any questions before we get started? Okay. So first of all, just really quickly, input-output impedances, also known as input-output resistances, if we're talking about the DC case. There's the first video you watch is where I talk at length about this, but the main thing to keep in mind is that if you are a voltage signal, you want to go into something that has a very high resistance, and you want to come from something that has a very low resistance. And if you are a current, and this is one of the weirdest things, if you are a current, you want to go into something that has zero resistance. And you want to come from something that has a very high resistance. And that seems to be the most counterintuitive thing. That students say, okay, my signal that's coming in is a current between 4 and 10 milliamps, or 4 and 20 milliamps. And so a lot of students think, okay, I'll just put a 100 ohm resistor at my input, and now that current becomes a voltage, and now that's great, right? Now my current's a voltage, and I'm just going to take the voltage and go with it. And that's not always a good thing to do. A lot of times, you don't want that current to have to see a 100 ohm load on you. And think about it. Think about the thing that's producing the current. If I'm producing a constant current, and some jerk down the line puts 100 ohms of resistance in my way, that means I have to provide a big enough voltage to keep maintaining that current, no matter what resistance they put. I'd rather they put 0 ohms of resistance, right? If you put 0 ohms of resistance, it's really easy for me to generate 20 milliamps. It's super easy, right? It's tough for me to generate 20 milliamps if you're putting a big resistance there. If you put a big resistance, yeah. So that's one of the biggest practical things. A lot of students don't like the idea of shorting something, right? They don't like the idea of my input is a short circuit because they think, oh, I'm going to break this thing. But not if the thing is providing a current. If the thing is providing a constant or a current as a signal, then a short is ideal. A short allows it to keep that current with no voltage effort at all. So, okay, so that's just a quick rundown again. You can watch me talk for 20 or 30 minutes in the video on that topic, and it's good. So the voltage amplifier, current amplifier, trans resistance, trans conductance amplifiers. Just also be aware that those exist and watch the video about that. So the main sort of focus point for the stuff that we go over today, for the problems we go over today, is this, that our ideal amplifier, which was shown as having 0 volts difference, 0 current, and a gain of infinite, that this actually is something more like it's actually something more like this. So in the non-ideal case, rather than having no current flow between these terminals, you will have some small current flow, as described by this resistor value RD. And rather than having an output voltage which doesn't change based on the load you connect to it, you will have an output voltage which does change based on the load you connect to it. Because the actual output voltage was produced by, or the actual voltage is produced by this internal dependent voltage supply. Hopefully people online can see here. We can, just in case we're too zoomed out to see this. All right, so people who are watching online, if we don't have the resolution, they can always freeze that and take a peek. So we have this some finite resistance here, and ideally this would be 0, right? Ideally there'd be no internal resistance, but there is some. And ideally this would be infinite, but there is some. And one thing you'll notice from the lab that you did last week is that modeling the inputs to the op-amp as a resistance isn't quite, that alone is not actually good enough to tell you what an actual op-amp does. Because an actual op-amp has input voltage offset, which means that both of these input voltages, when this is being driven to its steady state, when it's getting this feedback where these voltages are canceled out, it's possible for both these voltages to be higher or lower than the 0 reference. And so a lot of you saw that. A lot of you saw, right? It's possible to, for both of the, if one of these is grounded, or close to ground, or some connected to ground through some resistor here, you will have a voltage at this terminal that is not 0. And you'll have a voltage at this terminal that's not 0. So both of these voltages could be up at like a millivolt or at a negative millivolt. And it still has this sort of finite gain, but it's with this offset. So the behavior of offset isn't really reflected in the way this is shown, but it is an actual thing that happens in op-amp. So even this non-ideal model that we provide here, it's not a perfect non-ideal model. The problem with a perfect non-ideal model, though, is it's highly nonlinear, and we can't really touch nonlinear systems without making our lives really difficult. So we just don't do it. So we're assuming this kind of, it's ideal, but it's still workable, right? We can do any resistors, dependent voltage supplies. These are all circuit elements you can work with, right? We did dependent sources when you did 111 with me, right? Did we get to that? Yeah. So dependent sources, it adds a level of complexity to the circuit, but this is still not the worst thing in the world. To insert this circuit into our previous model is not the end of the world. We can still, almost every single problem in this homework set, as a worst case scenario, you could model a circuit using this as your example and solve it and get your answer. But what the book does is the book says, assuming this is the case, and assuming a certain thing, sometimes it'll assume that this is infinite, sometimes it'll assume this is 0, but it'll almost always assume that this is finite. The book sort of walks you through, let's assume this is the case, okay, now let's see how that affects our equations. And so the book kind of builds up this set of equations. It's not a complete set of equations, But the book looks through various scenarios and says, okay, what's the effect of these non-ideal properties on this overall amplifier design? And a challenge of using the book is it's an incomplete set of equations, and the equations that the book presents are very context-based. So the equations it uses for the overall gain of a circuit is dependent on all the junk that you connect around the op amp. It's not just for any case where we're doing an op amp that's modeled like this equation is going to be valid. It depends on what particular style of circuit the book was working with. So, okay. Any questions about that? About just kind of generally that non-ideal model of the op amp? Okay. Now, one of the biggest. Oh yeah. Okay. Now, one of the biggest, again, like I said, when you get to a problem in the book, it's a lot of it is, okay, what of these are they assuming are ideal? Sometimes they'll assume that's non-ideal. Sometimes they'll assume that and that's not ideal. Sometimes they'll assume all three of them are not ideal. So a lot of times what you have to do is when you look at the question, ask yourself when looking at the question 1, what section is this under? So if the question is under section 1.3, well, you're probably going to be dealing with the same scenario we were dealing with in 1.3. And also, if the question would need to provide you more information for you to find the answer, like if the question needed to provide you an open loop gain in order for you to answer it, and it doesn't, then you can imply that it's assuming an ideal case. Or if the question needed to provide you an RD for you to find some unknown, then you can assume probably that it's the ideal case if it didn't provide that to you. But again, these are only issues that you're going to run into parsing the homework in the Franco book. Midterms are going to be very clear what I'm asking for. Okay, so let's start looking through some questions. So first of all, I want to say question 1.6. So I'm not going to do question 1.6, but I'm going to give you kind of a hint. So question 1.6, basically the whole thing is based on when you have this finite open loop gain, we have this effect where the output voltage of our circuit is going to be that finite open loop gain times the voltage difference. So there will be some non-zero voltage differential between the terminals, and that will be multiplied by some finite gain, and that will produce your output voltage. And problem 1.6 is basically 4 different ways to slice and dice this equation. So don't overthink 1.6. 1.6 is basically how many ways can I ask you for the different parameters in this equation and have you give it to me. And that's the reason we're not going to really go into it, because it's fairly straightforward and it's fairly tedious. But just keep that in mind when you're doing it. 1.7 is a little bit different. So we're going to start by talking about 1.7. It's a nice sort of segue to this kind of structure here. So let me see 1.7. So 1.7 says, I'll just read it. An op amp with RD equals 1 mega ohm, so RD, that's here. Sometimes, honestly, I still have to go back and look at what they name variables in this book. So I like to, you can, the section 1.2, the little circuit they show, you can like blow that up and make bed sheets out of it or something and have it be really handy. Because I always have to go back, RO I pretty easily can remember. Sometimes I forget that RD is that non-ideal resistance between the input terminals there, but anyway. So an op amp with RD is equal to 1 mega ohm. So we'll just put that up here. It's a weird R. 1 mega ohm. And open loop gain is, so little a is, 100 volts per millivolt. Now, they're being a jerk here, right? So normally when you give little a as a parameter, the gain, you're just going to do 10 to the third, 10 to the fourth, 10 to the fifth. So when they do 100 volts per millivolt, right? So that's, right? Look at that. See? 10 to the fifth, right? So I don't know. And volts per millivolt is actually not I think volts per volt is probably the most common because when we're talking about this gain, it's already going to be an exponential form. It's usually so big that you don't have a choice. But well, I guess 100 volts per millivolt, maybe that does happen sometimes. RO equals 100. Okay. And it says it's driving a 2K load. So it's driving a 2K load. And then it says it's part of a circuit. Part of a circuit, it doesn't tell you what the circuit is, so that means you probably don't need to know to answer the question. Such that VP equals -2 millivolts and V out equals -10 volts. Sketch the circuit, find the voltages across and the currents through RD and RO. Make sure you indicate voltage polarities and current directions. What's the value of Vn? What's the value of V at the negative terminal? So it's basically telling us find everything that's going on with this op amp for this particular scenario. And the good thing is it says to, first of all, it says sketch the circuit. You'd have to do that probably anyway to do this. So so the first thing, before we just jump right into it, if I were doing this problem as a student, I would say, okay, which parameters did they give me? Finite open loop gain. Non-zero output resistance. Non-infinite input resistance. They're telling me there's some load resistance, and then they're giving me the voltage at the output of the op amp and the voltage at the positive input terminal. So based on all these parameters, it's suggesting to me that we're going to have to use a model for the op amp like this. So all of the non-ideal parameters that are shown in that non-ideal op amp model show up here. I'm not going to be able to get away from that when I draw my circuit. So we might just be able to kind of reset. Well, I kind of want to draw it a little bit bigger. But we're going to basically start from that. So I'll redraw it big. So it's 1 mega ohm. And then, so little a was 10 to the 5th. So we're going to have so when you say VD, that's the differential voltage, so that's VP minus VN. And then our output resistance was 100 ohms. I'm going to check and see if that's visible. It's on the threshold of being visible. I think it's still visible. And some more. We have a load resistor, 2 kilo ohms. And we know that the voltage at the positive terminal is -2 millivolts. Okay. Did we get everything? Oh, and the output voltage is 10. Negative 10. Oh, that's a big one. Okay. -10. Okay. So, one thing, first of all, that throws a lot of students is when it says the output voltage is -10, one immediate question a lot of students have is, wait, is it talking about here or is it talking about here? The output voltage actually refers to the voltage at the output of the op amp. So, in this case, it is the voltage here. which actually is the only way we're going to be able to solve this system, because knowing the voltage here tells us a little something about what's going on in here. It tells us a little, well, actually, no. If we had known this, it would have been super easy to do. But whatever, but still, we can do it. Okay, so how are we going? So it's asking for a lot. It's basically asking us to find the voltage and current through everything in this circuit. So we've drawn it basically here. And now it wants us to find the voltage and current through everything. Where do you think we should start? Maybe you have an idea for... Usually when I'm looking at a problem like this, there's not really a methodical way to do it. You really have to do the, well, what detail, based on what I know, what unknowns can I find? And you have to just start working your way through, what are the unknowns I can solve for right now? So what's an unknown that we can solve for right now? What's something, yeah?
Current at the output.
That's right, the current. So we know a voltage across a resistance. So we know V, we know R, we can find I. So we're going to be able to find the current. And the nice thing is, once we find the current, and I'll just solve for the current in this direction. Once we find that current, that's going to be really helpful working our way back in this circuit. So what's the current here? So I'm solving, now we've got to be very careful about direction. I'm going to solve for the current flowing out of the op amp. In this case, it's going to give us, it looks like it's going to give us a negative value, but just comfort-wise, I much prefer writing an equation for the current flowing out. So the current flowing in this direction, so that's the current flowing through this resistor here. It's always the voltage on this side minus the voltage on this side divided by the resistance. So this current I, making sure I don't go too far, I equals, the voltage on this side is negative 10 minus 0 divided by 2K. So that's going to be negative 5 milliamps. Still, yeah. So I'm just going to draw the actual value here. Now, a lot of times this is where students sort of say, well, so if it's negative 5 milliamps flowing that way, then it's actually 5 milliamps flowing that way. I usually stop myself as soon as I start to do that. As soon as I start to do the, well, I got a negative number, I want to get rid of that negative number. For me, it's more if I'm comfortable with the direction the current is flowing, with the way it's labeled, okay, I solve for the current in this direction, I just leave it as that. I didn't care what this value was. This value could have been an imaginary number and I wouldn't have really cared. All I know is I have a known current flowing in this direction. Let's not worry about the magnitude or the sign or anything else. Let's just say, assuming we know the current, how do we find the rest of this? So now that we know this current, what other detail can we solve for? Yeah?
Vn. Can you solve for Vn based off of like Vn?
We can, right, so we can solve for, that's going to be a couple steps ahead, but we can solve for the voltage here now, which will let us tell. So Vn and Vp give us, times this gain, give us the voltage here. And now that we know the current flowing through this little mini circuit, and we have a known resistance here, we're going to be able to find this voltage here. And then from that, we'll be able to find Vn. So there's a couple ways we could do this. There's a couple different ways we could do it. I'm probably just going to do it because we're able to. We don't have to write some big Kirchhoff's current law, Kirchhoff's voltage law. I'll probably just work my way back here. If we know the current flowing through this resistor, we can find this voltage drop, right? So we'll just find this. We'll just call this VRO. What's that voltage going to be? It's going to be 100 times I, which is going to be 100 times negative 5 milliamps, which equals negative 0.5 volts. So my voltage drop here across this resistor, negative 0.5 volts. Again, I'm not worried too much about the negative right now. As long as I know that I solve for the orientation in this direction. So now my question is, what's this voltage right here? In other words, what is 10 to the 5th times VD. What's the voltage across this dependent supply? Well, it's pretty easy to work our way back now. We can say, we know this voltage here, and we know this voltage here. So the voltage, by Kirchhoff's voltage law, the voltage across this has to be equal to the sum of these two voltage drops, right? We could have done it, if we were worried about orientation, we could have done it. But because I labeled it positive, negative here, the total of these two voltages is going to equal the voltage at the top of this source. So, and I don't know what I want to call that. Let's call it V. So let's call this. We'll call it V1. So the voltage there, this is going to equal this. So it's going to equal VRO plus V out, which is going to equal negative 0.5 plus negative 10 equals negative 10.5 volts. So now I know that internal in this op amp, this dependent voltage source is producing negative 10.5 volts. But now I know, right, that voltage was 10 to the 5th, or whatever, 100 volts divided by a millivolt, right? So it's 10 to the 5th times VD. So now I can say negative 10.5 volts equals 10 to the 5th VD. But VD, that's just the voltage differential. That's just Vp minus Vn. So that's 10 to the 5th times Vp minus Vn. And now look at this equation, right? Negative 10.5 equals 10 to the 5th Vp minus Vn. We already know one of these, right? We already know one of these values. So we know that Vp is negative 2 millivolts. Negative 0.002. So we're basically done. I mean, we're not done, but we have a little algebra to do here. But if we want to solve for Vn now, it's simply a matter of algebraic manipulation. So we can say, yeah, we can get low. So negative 10.5 volts divided by 10 to the 5th equals negative 0.002 minus Vn. So then we can say, so Vn, so moving Vn on that side and moving this on the other side equals negative 0.002 plus 10.5 divided by 10 to the 5th. My cell phone on me? Oh, I'm totally off the screen. Did I write off the screen? Oops. Okay. Let me just make sure. Let's all do it so we keep ourselves fresh. I gotta tell you, 5 o'clock feels real late right about now. That's like the long days. Gone off the screen again here. So what is that? Negative 1.895 millivolts, right? So, and one of the challenges with this is, one of the challenges here is that this was not necessarily a problem where we could have just, we couldn't have just fumbled through and found an equation that would have told us this directly. So to figure this stuff out, we really had to figure out which model of the op amp we're talking about, draw the circuit out, look at the circuit and say, okay, I know the voltage and the current, I know the voltage and resistance, so I can know the current. Once I know the current, I know that we kind of have to work our way back and think about it. Yeah, question?
So if we wanted to like double check this, we would just take the VN and VP and get the VP times by 8 to double check the RT outs, correct?
Yeah, yeah. Yeah. And this asks, so this problem asks for more stuff. I think it asks for like the current through RD and stuff. The current through RD though, that's kind of boring, right? I mean, you know the voltages of these, you know it's divided by, so the voltage difference divided VD divided by a million. So I'm gonna skip that part. You can do that for the homework assignment. Yeah.
The voltage difference, like VD, is that always going to be defined as positive to negative, or?
Yeah, the VP minus VN. Yeah, right. It'll always. Yeah. It's important to not mix up, especially since you can draw the op amp either way. You can draw the op amp with negative on top or positive on top. So it's really important to just to know that VD is always going to be VP minus VN. Yeah.
So if there wasn't a load, could we just use V out to find VD directly?
Yep. If there wasn't a load, then V out would equal this. Right. If there wasn't a load, then V out would be this V1 that I call it. Right. And then so you could just take, if there was no load, or if there was no load, or if you were dealing with the case where it's ideal zero output resistance, in either case, you could just say V out is equal to 10 to the 5th times the voltage differential. And actually, there's a couple problems where that is the case with the book, where the book tells you to assume a ideal output resistance, or you're just operating assuming that's ideal. This is probably the least common thing we deal with in terms of non-ideal behaviors is that. But yeah, so the stuff like the input current, you can calculate that. It's pretty trivial once we get to this point where we have pretty much all of our unknowns solved for. It's just a matter of Ohm's law to get the rest of the little pieces. Okay, any questions about that? Before I move on to the other one I want to talk about was problem 1.18. 1.18 is a little interesting because we're kind of taking a step back with 1.18. The book sort of does this, hey, you might have heard that op amps are ideal, but actually they're not ideal, and here's a couple of things that does. And then it says, oh, and also there's some wonky op amp configurations. Let's analyze them assuming it's ideal. So when you get to like 1.18, students are immediately like, well, what's the open loop gain? And it's not, it doesn't specify it, so you assume ideal. 1.18 is an ideal assumptions. It's basically just here's a wonky op amp circuit with positive feedback, which is one of the weird things, and it's saying basically analyze that. So let's do 1.18. At one point, and I think I asked you to just do part A of this. I don't really remember. You could do it either way. But so first of all, this is that dreaded, there's some positive feedback to this. But you can always, if you go back to, we did that example, I don't know if it was last time in class, I think it was on Friday, where we sort of analyzed an op-amp circuit, just sort of taking the circuit and treating the output as a voltage source and putting it in just like a circuit model, and we just analyze the circuit model. You can do that for this one. So if you're ever just more comfortable, just no matter how complicated it is, just making it a circuit like what you saw in the normal stuff in 111, and then analyze, or two circuits, right? Or in this case, it'd be one circuit. But if you want to just put it back into a circuit form and analyze it the way we did in 111, you can do that. You can always, that's always an option. So otherwise, if you're not doing that, just be warned that we sometimes play a little fast and loose with how we analyze the circuit. So we're not always as methodical as we are in 111, but that's always an option. If you're more comfortable with that and you're doing the homework, you can always go back to the more methodical approach. And I'll show you, if we have time, I'll show you how to do that. I'm not going to fully solve this all the way, but we'll get to part of it. So the issue here is, right, our normal op-amp analysis technique is write the ideal assumptions. And then our normal analysis technique is find the voltage at the positive terminal. Well, the problem now is we can't find the voltage at the positive terminal without knowing the output voltage. So we run into this challenge where we just have to, whatever, right? We can't solve it. We don't have a nice, clean set of independent equations, so we'll just have a variable in there. And we'll deal with it. And we'll go on from there. So what is the voltage at the positive terminal in this circuit? Well, the assumption that there's no current flow here is really useful. Because the assumption that there's no current flow here means that the voltage at the positive terminal is the voltage right here at this node. And because there's no current flow, what do we have here? We have an output voltage, and effectively we have a voltage divider. The 30K and the 20K make a voltage divider. So we can find the voltage at the positive terminal using the voltage divider equation, but just keep in mind that will be an expression as a function of VO. And that VO is not going to be solved. We're going to have to use that equation later on, add it to the pile of equations that we solved, but for now, we're going to have to just be comfortable with writing VP as a function of VO. And what is that going to be? So that is going to be VP. Oh, you know what? Just try to write it yourselves. I gotta wake people up. Write an expression for VP yourself. Otherwise, it's too easy. It's 5 o'clock. People's brains go on autopilot. I know how it goes. It's easy to say this looks easy, and then you'll do the exact same problem in the homework, and you're like, how did we do it? It seemed easy when we were doing it. Okay, that's good. So VP equals VO times 20K divided by 20K. Oh, yeah, 20K plus 30K. Right, somebody did 30K. Somebody did it backwards. Yeah. So we're just doing the. That's all. This is the mini circuit problem we're doing to find this, right? It's drawn weird, right? That's what throws people off. And it's also, we've got a wire here, but keep in mind, because there's no current flowing through here, so all the current flowing through the 30K flows through the 20K. So for all intents and purposes, they're in series. So technically there's a wire here, but because there's no current on that wire, these are series resistors. So we can do this, basically. Okay. So now let's look at the top part of the circuit here. So now looking at this top part of the circuit, we have an expression for the voltage here. We know that VP equals Vn, so we have an expression for the voltage here. The voltage here is given by this. So our question now is how can we possibly construct an equation to find to solve for V out based on what we know about the voltage at that node? Yeah.
Say it's equal to VO plus 10K times 0.3 milliamps.
VO plus 10K times Yeah, that's good. Yep. Right. So the point. So basically, this analysis said we know we got 0.3 milliamps flowing through here. So that means we know we have 0.3 milliamps flowing through this 10K resistor. So we know that. So we can basically say we have an expression for the voltage here. Then we can write, well, basically the voltage here minus the voltage here equals that 0.3. Yeah. Now, what if we didn't, now, that's nice because we had an actual value here. What if it just been this current, what if we just said this was I? We could also make this kind of the general case. We could say, that we could just write the expression for the current flowing in this direction, which is going to be this voltage minus this voltage, and just say that equals the current flowing in by Kirchhoff. So we could also just do that. Or we could treat it kind of like a node voltage in the same way. So yeah, let's just write an expression for this current I feedback. So I feedback is the voltage on this, I feedback in this direction is the voltage on this side minus the voltage on this side divided by 10K. That's V out times, oh wait, we can clean this up. What is that, 0.4?
Yeah.
So equals 0.4 VO minus VO divided by 10K. And that has to equal 0.3 milliamps. And so now we can solve for VO, right? So we can just say, so flop that 10K over, so we got so 0.4 VO minus VO, that's going to be negative 0.6 VO, is going to equal, multiplying that by a 10K, is going to be 3 volts. Whatever that is. -5. That feels right. If I were doing a test and I got a -5 there, I would say, all right, that's a nice whole number. I know Professor Lund doesn't like to, he doesn't like decimal points. He doesn't want to have to look at how many rounded decimals he did. So -5 sounds like the correct answer. That's usually when it's like like problems where like the doing it the wrong way gets you a clean answer. It's like those are tough to catch yourself. Okay, was that? I don't know if that was actually what it was asking for, but so, but now basically we can solve for, you know, I mean that was it. And actually, also keep in mind that if we had just called this an input, if this had just been a current input, we could have written an expression. We could have just left it. So we could have left this 0.3 milliamps just I, and we could have solved for this as an output as a function of I.
I'll double check.
We're good?
Yep.
Okay.
Plug back.
So what if we didn't like this? What if this all feels like voodoo? We just want to go back to 111? Don't we all just want to go back to 111? Well, no, that was remote. That was pretty bad. That was a bad quarter. Your group was 111. I was not sleeping at all that quarter. Jeez, that was a rough one. I don't want to go back to that. But let's say you did. Just really quickly, just so we have it on record on video, if you want to go back, how could we redraw this circuit? How can we redraw this as a collection of circuits we can analyze? There's one circuit. There's circuit number 2, and we know so we know the voltage here. So these are sort of our two circuits that we could have taken this circuit, redrawn it as these two circuits that we then analyzed just using whatever technique we prefer that we had done in 111. And actually, problem, if I had asked you to do part B for this says, repeat with a 40 kilo ohm resistance in parallel to the 0.3 milliamp source. So part B said, add a 40K resistor here. So what? We don't care. It's just a slightly more complicated equation now, right? So now, if I were doing this using 111 style, I would just do a Kirchhoff's voltage law analysis. I would say this voltage divided by 40K plus negative 0.3 milliamps plus this voltage minus VO divided by 10K equals this thing that I know, 0.4 VO. So it's actually, when you break it down like this, the part B of this is not that much more complicated. If you were trying to just sort of do it on the fly, it takes a little bit more thinking. So if you don't want to think about it, again, part B said to just put a 40K here. I don't think I asked you to actually do that, but if you wanted to, it's not that difficult changing it like that. Okay, we are at time, everybody. Thank you. Thank you, people online. Also, remember, all of you, if you glazed over something I did here, or, which I think probably a lot of you did, or if you were like, shoot, I didn't watch the videos in time and none of it made sense, you can always go back and watch these lectures or fast forward, skip the parts you don't like. Oh yeah, homework's in the back corner, please. Homework's in the back corner.
I turned in my homework online, if you prefer it enough. But
If you already have it online, I'd say just let it be.
it's right here.
Yeah, but then I'll grade it twice. I'll be grading it online. I'll be halfway through where you're at. Thanks, Bill. Appreciate it.
So this might not be.
Sorry. I didn't fully click there. Yeah, sure. Yeah.